This sequence of videos is going to continue to work with forces. Again, we're not quite to the meaty bits of doing all the calculations yet, but we're still building the foundation. And in particular now, we're going to try to understand how forces and mass relate, and really what's tying them together is acceleration. So this is two sections of night that we're covering here. And there's a few goals that we have. One is thinking of how forces relate to motion. Obviously, our first few chapters of this class talked about motion, and now we've been talking about forces kind of in the abstract. So now we're tying it together. So what we're learning about now does involve everything we've learned about in the first four chapters. We're going to define mass a little bit. Again, I expect that this is something that you've encountered before, that you're not too confused by. There's actually some really interesting subtleties here that I'll probably go on a tangent about. And we will define Newton's second law. Now, don't get worried that you've missed the first law. We are, in fact, going out of order. We will cover the second law and the 0th law in this sequence of videos. There are two big learning outcomes that it ties to. One is representing. We've been talking about vectors already with forces, so that's still coming in here. But then the second thing is we'll talk a little bit about some plotting, the plotting relationship between, say, force and acceleration, or force and mass. We're also going to talk about some nice mathematical techniques related to proportionality. So what we do here with proportionality is actually true in general, not only for forces. So when we're talking about representations here, thinking about plots, this is something generally true, not only for forces. And then again, problem solving keeps popping up, especially here. We are meeting Newton's second law, and this is going to be the foundation of our calculations for the next few chapters. So we're not quite doing the calculations yet, but the understanding that you'll have from this material is really important for the future problem solving you'll do. So first, we're going to think about an experiment. Now, feel free to actually grab some rubber bands or non-latex bands if you have them, and otherwise we just have to think through this. So one thing to point out with rubber bands is that they're actually a little bit complicated. That the force that the rubber band exerts, and if you stretch it between your fingers and you consider, remember, only consider one object, if we consider the right hand, our object, we think about the force that the band is exerting on our finger, and you would feel that pull, right? Now, the pull that you feel depends on the length of this. So as you move your hands closer together or further apart, you actually feel a different pull from the band on your finger. So what that means is that for this experiment, whether it's real or not, you have to keep the same length the entire time. And again, we're not just going to be stretching rubber bands between our fingers here. We're actually going to do something more concrete with it. But that length always has to be the same. That's important. Now, one thing that you could again try, or just believe me when I tell you this, is that if you have identical rubber bands, obviously some rubber bands are different than others, which is fine, but identical rubber bands, if you put two rubber bands on between your fingers, you keep the length the same, again that's important, you would feel a bigger force. Now, our fingers aren't exactly calibrated instruments, so you might not be able to tell that it's exactly twice the force, but we do actually have devices for measuring force, and they would tell you, in fact, it is twice. So, as we keep adding rubber bands, we keep increasing the amount of force. So n rubber bands, where n is, say, 2, or 3, or 100, whatever, is n times the force from one band. So we see that this happens. Again, this itself isn't that exciting, but let's now try to move forward with this experiment to understand motion, right? No motion was happening here. Now, let's imagine a block which has a mass of 1 kilogram, and again, I haven't defined mass yet, but we'll get there. This is our object. This is the thing we're interested in. Now, we're going to have to put it on a low friction surface for this to work. So, say ice. Imagine this is ice. Or an air hockey table that's turned on, so there's little jets of air that make it move around really easily. Because right now we only want to think about the rubber band. We don't want to think about friction, so we need this surface to not have friction. So ice is a good example, or an air hockey table. Now the question is, how is the block going to move? And now again, we have to maintain this constant stretch. So as the block moves a little bit to the right, my hand has to also move to the right so that the rubber band stays stretched the same length. And the idea in this case, again, remember that the block is our object, and so what we would have is a force from the rubber band pulling this way. So I could call this F pull, for instance. And we'll keep it stretched the same, and we want to ask, how will the block move as a response to this? Now, again, most of us don't have frictionless surfaces just sitting around, so you can't necessarily do this experiment. But this is really important because this is one of the few places where your intuition might actually mislead you a little bit. So let's go through what's going to happen. What we're going to see, the block starts over here, right? So this is our initial position, this is our final position. And again, we've maintained this stretch the entire time as it started from here to over there. And what we see is that it starts moving, of course, if it started from rest, and it actually keeps going faster and faster. So if you pull at a constant speed, this will actually catch up to your hand. That would mean that the rubber band changes its length. So to maintain this constant stretch, you actually are accelerating the block. So this is something that, again, might seem not true. And the reason for that is because of the lack of friction. So this is something important, that once there's friction, if it's a lot of friction, this might not seem like that's the case. And there's kind of a neat experiment that you can actually do. And instead of using a rubber band, you can use a little handheld force scale. And that will actually help show you what's happening. And in that case, even if there is friction, you can still see that a constant force results in acceleration. And in this case, our acceleration is uniform. So this is what we would kind of see happening over multiple moments in time, and we generate a motion diagram for that. So we could repeat this experiment over and over again using different numbers of rubber bands, which gives us different forces. And we would see that this would result in a different acceleration. Now, one thing to note here is that acceleration is constant for a constant force. So as long as you keep that rubber band stretched the same length when you do this, you actually get an acceleration that is constant. It's not changing from one position or moment in time to the next. So as we add more rubber bands, we would get more acceleration. Now, one thing that's kind of trivial but does show up in our plot is that if you had no force, you would have zero acceleration. If the block was sitting there at rest and you didn't pull on it with the rubber band, it would continue to sit there. So that means the intercept of our plot here that we're making is at 0. Now, in this case, we've labeled a few places where the rubber bands are related to the acceleration. Now note that A1 here isn't specified. This is just the amount of acceleration that you got from one rubber band. And if you use 2 rubber bands, you would get twice that acceleration. 3 times the rubber band, 3 times that acceleration. So even though we're not plugging in real values here, we can still see that this is a linear plot with an intercept through 0. And this is a really nice relationship. When you see a plot like this, this is a relationship of proportionality, which I'm going to talk about next.